Hello all, I'm sorry for taking 2 months since the last video. I was traveling, actually working abroad, so I had to take a break from these videos because I had to work on something else. So I owe you the last topic for Unit 5, which is topic 11, which deals with astrophysics and cosmology. This is arguably the chapter in the unit that students find the most interesting, but I hope I get to do a good job in delivering these notes. So we will start with the gravitational field, which resembles, as you will see, Coulomb's law and the electric field and things like that. And then we will continue with stars and the formation of stars, the death of stars, the lifetime of stars, and so on. So the first part of topic 11 is topic 11a, titled Gravitational Fields. And I think I'm gonna break this topic into several videos because there is a lot of material. So let's talk about gravitational fields to begin with. So the gravitational field is responsible for the accretion of mass together after the Big Bang. So you can imagine the universe as being kind of like dust in the beginning because there was a huge explosion that started the universe, and gravity was this force that was responsible to put everything kind of like back together. So the formation of planets, stars, and the accretion of matter into larger objects is solely due to gravity. Okay, so as far as we know. Now someone will say, why not electricity? It's not electricity, even though electricity is one of the strongest forces, actually the second strongest in the universe. Electricity cannot do that simply because most objects in the universe are electrically neutral, because you have as many protons as you have electrons in each atom. Therefore, most objects are usually electrically neutral. So now, why do I keep mentioning electricity? It's because gravity resembles electricity in that it's an inverse squared law, but it's always attractive. So let's write this down. So the gravitational field, or gravity, is an attractive force which resembles Coulomb's force. Let's immediately proceed with writing down the force of gravity and the force of electricity, known as the Coulomb force, to see what I mean. So this is the force of gravity between two masses of mass m1 and m2, separated by a distance r, and the subscript n stands for Newton's law because it was discovered by Newton after studying the Kepler's laws of motion. And the Coulomb force, which we already covered, is K Q1 Q2 over r squared. So notice also that we have a minus sign for Newton's law, which signifies that this is an attractive force, whereas the Coulomb's force can be either attractive or repulsive. And you see how the two laws are related. If we change, let's use black. If we change K, the Coulomb's constant, with G, the gravitational constant, and if we change charge with mass, the two laws are pretty much equivalent. If we have a mass m1 and a mass m2 separated by a distance r, then the mass m1 will feel an attractive force Fn towards mass 2, and m2 will feel an equal and opposite force Fn towards mass m1. Therefore, the Newton's law of gravity also obeys Newton's third law, which tells us that if an object exerts a force F on another object, then the other object also exerts a force F on the first object, okay? Now, the force of gravity works on anything that has mass. So, for example, neutrinos that are kind of massless do not really feel the force of gravity, okay? Subatomic particles do feel the force of gravity, but for subatomic particles, because they are so tiny, other forces dominate them. So the strong force mainly and the electric force, okay? Now, the gravitational field strength, okay? So the gravitational field strength is our familiar G, okay? I'm gonna write it down later. So the gravitational field strength at Earth's surface is G equal to 9.81 newtons per kilogram. Okay, so this is analogous to E, which is the electric field strength. Which is measured, let me use a clean line, measured in newtons per coulomb. Okay, so what does the gravitational field strength G tell us? That if I have 1 kilogram of mass at the Earth's surface, it's going to experience a force of 9.81 newtons. Just like if I have 1 coulomb of charge near an electric field that has a strength 5 newtons per coulomb, that charge of 1 coulomb is going to experience a force of 5 newtons. Okay? And we will come back to G later, okay? So it might come as a shock, but G is constant only on the surface of the planet. So as we move up, it gets weaker, as we will see. So, but before we say that, let's also say that masses set up gravitational fields which is a vector quantity everywhere in space. I have to do something about my handwriting. Sorry, guys. So what I mean is that let's say we have a large mass m. Maybe this is a planet. Maybe this is a star. Maybe this is Earth. Maybe this is the sun, etc. So this mass creates a gravitational field. Okay. And the gravitational field is G pretty much, okay? So it's what we call G, okay? Maybe I'm gonna leave it there, okay? And this gravitational field points inwards, okay? So this is like the electric field lines we've seen when we studied the electric field, okay? So these lines are perpendicular on the surface. So this is a sphere, so these lines are perpendicular to the surface, okay? So the purpose of this gravitational field lines is that if we have a mass m, kind of like a test mass, so the big M is like a planet, maybe the small m is like a, I don't know, a basketball ball or something like that. So a small test mass in this field will move inwards. Okay, so this is similar to the small test charge we use to study electric fields. Okay, so this is analogous. The only difference is that the gravitational fields are always attractive. Okay, so masses move towards each other. Now, perpendicular to the gravitational force, to the gravitational field line, sorry, are the equipotential lines. Equipotential, sorry. Lines. So if I have a large mass M that sets up electric field lines, okay, that are perpendicular to this mass, to this sphere. Oops, it has to point inwards, I'm sorry. Then let's use a different color, maybe, what kind of color? Let's use green, okay? So perpendicular to these lines are equipotential so-called surfaces or lines, okay? So maybe let's use number 3 for this one, and maybe let's use number 2 for this one, and maybe number 1 for this one near the planet. Okay, so everywhere on this equipotential surface, an object of mass m will have the same energy, pretty much. The same happens for an object along this line 2. Same happens for an object along this line 1. So no energy is needed to move an object along an equipotential surface, pretty much, or along equipotential lines. But we do need energy to move objects of some mass m between these equipotential surfaces, okay? And the reason why I number these equipotential surfaces is that let's say that you need 10 units of energy to move from equipotential surface 1 to 2. Then you also need 10 units to move from equipotential surface 2 to 3. And you see how the distance between 1 to 2 is, say, 10 kilometers, whereas the distance between 2 and 3 is maybe 100 kilometers. So equipotential surfaces move apart in the sense that for the same amount of energy, we can cover more distance as we move away from the mass m that creates the gravitational field, pretty much, okay? Which kind of makes sense, okay? Now, let's write all this down. So, no energy needed to move along an equipotential surface. Energy is needed to move across equipotential surfaces. And in the example we showed, this means for moving from 1 to 2, or maybe from 2 to 3, or maybe from 1 to 3, and so on. Now, as we move away from the source, less energy is needed to move. Therefore, equipotential surfaces grow apart in the sense that for the same amount of energy, we can cover more distance. Okay, so again, let me draw another surface. Let's call it 4. Equipotential surface 4 is out here, okay, really far away from the source. So if assume that we need 10 joules, okay, it's not going to be 10 joules, but let's assume it's 10 joules to move a mass m from equipotential surface 1 to 2, then also 10 joules will be needed to move the same mass from equipotential surface 2 to 3, but you see how the distance between the equipotential surface 2 to 3 is larger than the distance between the equipotential surfaces 1 to 2. And then the same can be said for moving the same mass m using 10 joules from equipotential surface 3 to 4, which kind of exaggerates, but shows my point that equipotential surfaces grow apart, okay? Now, another important thing is that near the surface of the planet, we get an approximate uniform field. So we can assume that we get an approximately flat field. And what I mean by that is that, let's say that this is the surface of the planet, and this is the equipotential line. You see that the field here is kind of uniform, meaning that it's constant because G changes by very, very, very little near the surface of the planet. So when I say near, up to around 50 kilometers, say, don't quote me on that, we have to do the calculation, but something like that. So for the first 10, maybe 50 kilometers from the surface of the planet, the field is uniform and flat, meaning that it's the same, okay? I mean, the same in the sense that G is about 9.81 newtons per kilo or 9.81 meters per second squared. The two are equivalent, by the way, and we can prove it. I didn't prove it yet. So newtons per kilogram, which we use to express the gravitational field strength, can be broken down into 1 newton is 1 kilogram times 1 meter over second squared. And then we have to divide by kilograms. So you see that newtons per kilogram is equivalent to meters per second squared. Okay. Now, what's next? Let's define G, okay? G is defined, the gravitational field strength, and this applies to any object that has some mass, okay? G is equal to the gravitational field constant times the mass of the object over the distance squared from the object, okay? And it's measured in units of newtons per kilogram. We already mentioned that. And this is, I'm gonna write it with red color, so it's equivalent to the electric field strength, which is given by K times Q over R squared. Remember that any, and this is measured, actually let me make some space. This is measured in newtons per coulomb. Okay, let me give you the gravitational field strength or constant. It's given by 6.67 times 10 to the negative 11 newtons times meter squared over kilograms. And notice how much weaker this constant is compared to K. Let's write this down actually. K from electricity is 8.99 times 10 to the 9 newtons times meter squared over coulomb squared, and here I need kilogram squared. I'm sorry. So yeah, pretty much this tells us that the force of electricity is about 10 to the 20. Actually, it's more than that. But anyway, the force of electricity is much, much larger than the force of gravity. Now, let's go and use this. Let's do an example. So let's use G to calculate the gravitational field strength. So calculate, actually, example, G at the surface of Earth. Okay, at the surface of the Earth, r, little r, is equal to the radius of the Earth, which is 6,371 kilometers. And also we know that the mass of the Earth is 5.97 times 10 to the 24 kilograms. So if we plug everything in, we will find that G is 6.67 times 10 to the negative 11 times 5.97 times 10 to the 24. And I think I mentioned it in other videos. Remember how I put the numbers to the left and the units to the right, so the units come here on the right. So the gravitational field constant has units of newtons times meter squared. Actually, I don't have enough space, so I'm gonna go on a new line. So newtons times meter squared over kilogram squared, and then the mass of the Earth has units of kilograms. And then we have to divide this expression by the radius, which is 6 million, actually, 371,000 meters. Remember that we have to convert to meters, and that's squared. So here I need meters squared, so meters cancel, and the kilogram on the numerator cancels. And if we do all the calculations, we find that G is exactly 9.81 newtons per kilogram as expected. Okay, this should come as no surprise. Now, the next thing I want you to be aware of is the variation of G with respect to small r, where r measures the distance from the center of the Earth. So variation of G with r from the center of the Earth. So if we make a plot, this looks like this. So if this is r, this is G, this is 0 at the center of the Earth, and this is r equal to the radius of the Earth, which is 6,371 kilometers. So let's measure the r in kilometers, and G is measured in newtons per kilogram. This is 9.81. Okay, so one data point is this. At the surface of the Earth, G is 9.81 newtons per kilogram. So we get the 1 over r squared fall off away from the center of the Earth. From the surface of the Earth. But inside the Earth, G increases linearly. Okay, so this is inside Earth, and this is outside of Earth. This is not something you are required to know, but in some special questions at the A-level test, they might actually ask you to comment on something like this. Why is G increasing linearly with the distance from the center of the Earth? And the reason is the following. So G is actually, let's say G is proportional to mass over r squared. But what is mass? Mass is density times volume. So this is proportional to density times r cubed, right? Because the volume of a sphere is 4/3 times pi times r to the cube. So if we combine these two, we see that G is actually proportional to the density of the Earth times r. okay? But the density, if we take it as a constant, which is not actually, but for the sake of the argument, we can take the density of the planet to be uniform inside the Earth, then we see that G increases linearly with distance from the center of the Earth. So this is the explanation. And also another thing that is important is that at the center, G is actually 0 because G is proportional to the density times R, and if R is 0, oops, then G is also 0, right? And we can also see this, like if we are at the center of the Earth, you kind of like have pressure, equal pressure from everywhere, from the mass above you, and all these forces cancel out pretty much, so no force at the center of the Earth. So another thing that is kind of like cool trivia that can come up as a problem at the A level is the field strength is a vector. So for two planets, there is a point where the two fields cancel out. And the two fields are the gravitational field of the planet and the gravitational field of the other planet, okay? Where the fields cancel out. Okay, let's study this situation. So let's say, actually, let's use a clean page. So say I have a planet of mass m1 and a planet, maybe it's smaller, of mass 2. Okay, this is the distance between them. Okay, let's call the distance between them as d. And as we claim, there is a point where the two fields cancel. Okay, so this point is at the distance r1 from mass 1 and at the distance r2 from mass 2. Okay, so to find that point, we have to set the two gravitational fields as equal to each other. So at this point, the gravitational field strength of planet 1 is G m1 over r1 squared, and this must be equal to the gravitational field at the same point from planet 2, and that field is given by gm2 over r2 squared. So G cancels, and this is r2 squared, by the way. So we have to have m1 over r1 squared equal to m2, and for r2 we can use d minus r1 squared, okay? Because notice that r1 plus r2 is equal to d, so r2 can be written as d minus r1, okay? So a little bit of algebra here. We bring d minus r1 over r1 squared to the left hand side, and this has to be equal to m2 over m1. So we see that d minus r1 over r1 must be equal to the square root of m2 over m1, and we want to solve for r1, okay, because we take the distance between the two planets as something that is kind of known. So we can write this as d over r1 minus 1, okay, is equal to the square root of m2 over m1. So we can take 1 to the other side. So d over r1 is 1 plus the square root of m2 over m1. So r1 is then given by d over 1 plus the square root of m2 over m1. Okay, and yes, this is what I wanted to say for the point between two planets where the two fields cancel. So if you put an object there, it's not gonna feel any force pretty much. Okay, now if mass m, the importance of the gravitational field is that we use it to express forces pretty much. So a mass m, which is generally much smaller than the big mass m, inside a gravitational field of strength G will experience a force F equal to m times G. And since we know that G is given, little g is given by big G times big M over R squared, then we see that this force is equal to G m over R squared. Okay, and this is the Newton's law of gravity. Now let's talk about another concept. So recall that work is force times distance, right? And work has units of energy. So in a radial field such that the field depends on 1 over R squared pretty much. Okay, this is what a radial field means, that things change as we move radially outwards from something. Okay, so in a radial field, the potential energy, the gravitational potential energy, is given by G m over R pretty much. Okay, how do I know that? Because it's force times R, so G m over R squared times R. Okay, now this is different from the mgh you guys are used to, so let's address that. So note gp, which is this pretty much, this is the gravitational potential energy, right? So gp is equal to mgh only applies if G is taken to be a constant. Okay, this is true near the surface of the Earth. So in general, up to 50 to 100 kilometers from the surface. Okay, so what I'm trying to say is that if I take a rocket, and again, rockets are made by my friend Elon Musk and SpaceX, I guess. So let's say I get one of those rockets that self launch or something like that, and I travel like 2,000 kilometers away from the surface of the planet. Then G is not gonna be 9.81 there. It's gonna be much less. Not much less. I think it's gonna be like you can calculate it, but it's not gonna be 9.81. Maybe it's gonna be 8 point something. So But for example, commercial airlines fly at a height of 36,000 feet, which is about 10 kilometers. So the force of gravity they experience is about the same as the force of gravity you experience at the surface of the planet. And I'm gonna provide an optional proof for that. You don't need to know this, but it's cool. I mean, if you want to become a physicist, I mean, study physics later in your lives, it's good to know these kind of proofs. Okay, let's provide a proof for what I said. So optional, we will basically prove that GP is indeed mgh only near the surface of the planet, because the general expression is this one, G times big M times small m over R. Now, let's start with GP given by mgh, but what is G at the height h from the surface of the planet? It's going to be big G times the mass of the Earth over the radius of the Earth plus h, and the whole thing should be squared, okay? And then we still have the h on the numerator. Okay, let's bring all the constants to the left hand side. So big G times big M times small m, okay? And then we have h over r Earth plus h squared on the denominator. Now this can be written as h over, we can take r Earth as a common factor, and in the parenthesis we're gonna have 1 plus h over r Earth and the whole thing squared, okay? Hope this makes sense. If we multiply re with 1, we get r Earth back, and if we multiply big R e times h over re, we get h back. So we haven't done anything, pretty much, okay? Now let's keep working with that. Since our Earth is a constant, we can bring it outside of that thing and recover G times big mass times small mass times over our Earth squared, okay? And notice how this is nothing else but G at the surface of the planet, right? And then we have to multiply by h over 1 plus h over r Earth, and the whole thing squared. Now, if h is much, much smaller than the radius of the Earth, then h over r Earth is approximately 0. So therefore, GP is mgh near the surface of the planet, okay? And you can prove this for yourselves. So as we said, our Earth is 6,371 kilometers. So let's say that we are 100 kilometers, oops, not kilograms, kilometers, I'm sorry. So let's say that we are 100 kilometers from the surface of the Earth. If we divide 100 by 6,371, we find 0.015. This is a very small number. And then we have to take pretty much in that denominator over there, we will have to take 1 plus 0.015 squared, and this is going to be equal to 1.03. Okay, so you can safely say that up to about 100 kilometers, G is constant. So for a plane that flies 10 kilometers above the surface of the Earth, the gravitational field is almost the same as the one we experience here down on the surface of the planet. Okay, this is an optional proof, but it's a cool thing to know, I think. Now, we can also define a gravitational potential, which is a scalar quantity, just like the GPE is a scalar quantity. So we can define this by dividing EP, which is the gravitational potential energy, with the small mass m. To find V, okay, we use V just like in the case of the electric potential. V is minus G times big mass over R. And this is measured in joules per kilogram. And the importance of this is that if we have 1 kilogram of mass, then the work needed to move that 1 kilogram from an infinite distance to the point R is given by 1 joule. Okay, so let's write this down. V represents the work required to bring a mass of 1 kilogram from R equal to infinity, where V is 0 by definition, right? Because if we divide 1 by infinity, anything by infinity, we get 0, okay? To a distance R, okay? It is analogous to V equal to K Q over R for the electric potential. So you see that anything you know about the electric potential applies to the gravitational potential pretty much, okay? So let's talk about the Earth's equipotential surfaces. So basically, we will calculate what the gravitational potential is at a certain distance from the center of the planet. So to do that, we start with the definition of the potential, which is minus g times the mass of the Earth over the distance from the center of the Earth, and simply solve for r, okay? So this is given by minus g m over v, okay? And if we plug in constants, we have 6.67 times 10 to the minus 11 for the gravitational constant times 5.97 times 10 to the 24 kilograms for the mass of the Earth over V. Now the units for the mass of the Earth is kilograms, for the gravitational constant it's newtons times meter squared over kilograms squared, and then we have joules over kilogram for the value of the gravitational potential. So kilogram squared with kilogram squared cancel, and recall that 1 joule is 1 newton times 1 meter, so the units work out to be meters as expected. So R is given by minus 4 times 10 to the 14 over V meters. So this is the distance from the center of the Earth, okay, where an equipotential surface is. So what I mean by that is that let's say that we want to find the distance from the center of the Earth where the gravitational potential is V equal to minus 60 megajoules over kilograms, okay? So if we plug in numbers, we will find that R is minus 4 times 10 to the 14. By the way, and this is minus 60 times 10 to the 6 joules per kilogram. So we substitute that into the denominator. So we find minus 60 times 10 to the 6. And this should be meters. And if we do the calculations, we find that at a distance of 6,667 kilometers, the gravitational potential is minus 60 times 10 to the 6 joules per kilogram. So at that distance, we have our first equipotential. Now, if V is minus 50 megajoules per kilogram, then the radius works out to be 8,000 kilometers. Okay, and if V is minus 60 megajoules per kilogram, the distance works out to be 10,000 kilometers, okay? So you see how we get an increase of 10 megajoules per kilogram in the potential, but the increase in the radius is much larger, meaning that the equipotential surfaces grow apart. So if we draw this, what we will find is, if this is the Earth, okay, let's make it small, then the first equipotential that we found with V equal to minus 60 megajoules per kilogram is, say, there, and this distance from the center of the Earth to the first equipotential is 6,667 kilometers. Then at 8,000 kilometers, so somewhere there, say, we will find the second equipotential, okay, with V equal to minus 50 megajoules per kilograms, okay, and at 10,000, so somewhere here, say, so 10,000 kilometers, we find the third equipotential, which is minus 40 megajoules per kilogram. So what do these numbers mean? If we have 1 kilogram, so let's say that we have a mass of 1 kilogram at the first equipotential, we will need 10 megajoules of energy to move it by, what is it, 8,000 minus 6,667 kilometers. That's what, 1,300 kilometers. So actually, let me calculate it. 8,000 minus 6,667. Yeah, it's 13. So 1,333 kilometers. So we will need 10 megajoules to move that mass by pretty much around 1,300 kilometers. And then once we are out there, so if this mass is here, mass of 1 kilogram, okay, then we will need another 10 megajoules to move it by 2,000 kilometers now. So you see how the same amount of energy makes the mass move by a much larger amount of distance, okay? And this is what I wanted to say. Let me write a few notes before moving on. So equipotentials grow apart. We will repeat what we wrote before pretty much. So equipotentials grow apart in the sense that it takes the same energy to move a larger distance as V decreases. What do I mean by that? Sorry, actually increases. Oh my God, sorry, made a mistake. V increases. I'm sorry. So if we are here at the first equipotential, the potential energy, the gravitational potential is minus 60 megajoules per kilogram. But if we are over here, it's minus 40, and minus 40 is larger than minus 60. Remember that when we deal with negative numbers, a smaller number in absolute value, but negative, is actually larger than a larger number in absolute value. I hope this makes sense. So minus 40 is actually greater than minus 60, okay? And 0 is greater than minus 40, of course. Okay, other thing I want to mention before moving on is that for spherical masses, we can take the whole mass to be concentrated at a point in the center. So what I mean by that is, if we have a mass m that creates a radial field that points inwards, as we said, right? This is equivalent as having a point, literally a point, with mass m creating the same field, okay? And you have to imagine that all these lines focus on the center. So And another thing is that V is 0, so the gravitational potential is only 0 at r equals to infinity. So there is no in between, there is no point between two masses where the potential is 0. And this is a consequence of the fact that V is minus G times M over R. So it only takes one value, negative. Whereas for the electric potential, we can have a positive electric potential and a negative electric potential. So there are areas between two charges. So what I'm trying to say is that if we have a charge plus Q and a charge minus Q, there is a point in between them where the potential, the electric potential, let's call it V electric, is 0. Whereas if we have two masses, M1 and M2, there is no point between the two masses where the potential is 0. The only point in space where the potential, the gravitational potential is 0 is at infinity, okay? Which is obvious from the 1 over r dependence. If r is infinite, then 1 over infinity is 0, so the potential is 0, okay? Now, let's switch gears and talk about an application, sort of gravity in satellites, okay? So the next topic, semi-topic, I guess, I mean subtopic, sorry, is satellites, okay? Satellites, and I love satellites. And again, we can think of our friend Elon Musk, who deals with satellites, and NASA as well, and ESA, and now there are other space agencies. China, India has have space agencies, and so on. Forgive me if I'm forgetting anyone, but I guess these are the big players. Japan as well. So satellites are also known as space junk. I think currently the amount of satellites out there in low Earth or geostatic orbit are like, I think, in the thousands. I want to say 10,000. I'm not sure. Check it out. So something like that. So thousands of satellites are out there. They are used for communication purposes, TV, spying, taking photographs, and stuff like that. So let's design, let's make a scheme of what's going on. So if this is the Earth or any other celestial object, I mean, it works with them as well. And this is a satellite of mass m in circular orbit around the planet, okay? Then if this is the distance r, then the gravitational force acts as the centripetal force that keeps the satellite into orbit, and the velocity is tangent to this circular motion, okay? So whenever we have, remember that if we have a force perpendicular to the speed of an object, we have circular motion. Okay, so let's go see. So if you have circular motion, we have that the force is equal to m times the angular acceleration, which is given by v squared over r, and r is taken from the center of the Earth, okay? But, okay, what force keeps the object in motion? In this case, it's gravity or Newton's law, so G times big M times small m over r is equal to mv squared over r, okay? So you can cancel off, sorry, this is the force, so it should be r squared. So you can cancel the r there, we can cancel the mass of the satellite. So the velocity is given by the square root of g times m over r. So v only depends on r from the center of the Earth. If let me help you here. If they mention height from the surface of the Earth, so I mean in a problem, if they mention h from the surface, then r is going to be equal to the radius of the Earth plus h, where the radius of the Earth again is 6,371 kilometers. All right. Okay, so another thing though is that remember that in circular motion we can also find a period or an angular speed. So let's go do that. So also g times m times small m over r squared is equal to m omega squared times r. So the mass of the satellite also cancels. So we get g m over r cubed is 4 pi squared over t squared. So t squared, the period, which is the time needed for one orbit around the planet, is 4 pi squared over g times the mass of the planet r cubed. So we see that the period squared is proportional to the cubed radius, which is also known as Kepler's law. Okay. Remember when we said that Newton discovered the law of gravitation by studying Kepler's law? So this is one of these laws. So if r increases, then the period for one revolution increases, but the velocity actually decreases, because remember that the velocity is inversely proportional to the square root of 1 over r. So the farther away we are from the Earth, the slower the satellite moves. Okay, now let's go calculate a few more things before closing this topic, this chapter, this video. So let's talk about geostationary satellites, or geostatic as they are known. So geostationary satellites have a period of t equal to 24 hours. So they stay at the same location around the equator. So these satellites are used for communication purposes, because you have to synchronize, I think it has to do with something like that. You have to synchronize the signal that is sent by someone and it's reflected on the satellite somehow and so on. So you need it to stay stationary at the location. So let's go find how high up these satellites travel. So we're going to use this equation that we just derived. So, but we will solve for r cubed. So r cubed is g times m times t squared over 4 pi squared, okay? And if we plug in numbers, we will find that r is 42,290 kilometers from the Earth's center. Okay, so let's go find the height. Remember that the height plus the radius of the Earth is equal to the r that we found. So the height from the surface of the Earth is r minus the radius of the Earth. And remember that the radius of the Earth is 6,371 kilometers. So we find 35,919 kilometers, which is about equal to 36,000 kilometers, which you will find quoted if you Google height of geostationary satellite. Okay. Now There are also low polar satellites. Okay, these do not move around the equator. They instead move from pole to pole, So they move from pole to pole near the Earth's surface. So their height is about 200 to about 1,000 kilometers. And they are just outside the atmosphere. Now, the final concept I want to discuss is the concept of the escape velocity. So if we give an object enough energy or enough speed, it can escape Earth's gravity from the surface of the Earth at h equal to 0. So how can we find that? At the surface of the planet, we have a gravitational potential energy equal to G times M over R, and this must be equal to 1/2 mv squared, okay? The mass of the object cancels, and to find this v, we have to calculate the square root of 2 times G times the mass of the Earth over the radius of the Earth, okay? Where this R over here is our Earth, because we are at a height of 0 from the surface, okay? So if we plug in numbers, we find that this is equal to 2 times 6.67 times 10 to the negative 11 times 5.97 times 10 to the 24 over 6,371,000 meters for the radius of the Earth. So this escape velocity for the Earth is 11.2 kilometers per second. Okay, this is a very well-known result, and as an exercise you can actually try to find the escape velocity from the solar system. So to do that, you have to use the mass of, you have to think about that, and the radius of something else that you need to think about. All right, so this is it for topic 11a, which deals with gravitational fields. In the next video, I'm gonna talk about stars and such. I hope you guys enjoy these videos. I hope they are useful. Let me know what you think about them in the comments, and like and subscribe and so on. Cheers.